So here we are at the second part of the chemical context of life videos. We're going to talk about building molecules today. So welcome back if you're coming back in and for some reason decided to I don't know, just binge all of these videos. Oh, it might be right before an exam. That might be it. So good luck on that. But if you're here for other reasons, um, we're going to be building molecules today, or at least not building molecules. You're building molecules all the time in your body. We're going to be to see how molecules are built. So what is a molecule? A molecule is two or more atoms that are bonded together. They could be complex or they could be more simple. You can see ozone right there, O3, made up of three distinct um, oxygen atoms. And that's compared to the molecule on the left that has different types of atoms. So both of these are types of molecules bound together. Compounds are molecules that have two or more different kinds of elements involved in them. So that ozone we just saw is a molecule because it has bonds, but it's not a compound because all of the atoms in it were ozone. Here you can see different types of compounds. Water has two types of elements, oxygen and hydrogen. Carbon dioxide has two types of elements, carbon and oxygen. Ammonia has nitrogen and three hydrogens. Methane has carbon and hydrogen. These are compounds because they have multiple different types of elements involved in them. Oftentimes when we're looking at molecules, we're going to look not directly at the molecule. You need an electron microscope to do that. So we just want to know information about the molecule. And we can get that from a molecular formula. The molecular formula will have the element name, and you found that on the periodic table of elements. The elemental symbol that you found with the name on the periodic table of elements. So here we have C, and we know C is carbon. H is hydrogen. O is oxygen. And then you're going to have a number next to it. Now, these numbers are different than the numbers that are on the periodic table. So C6, if that's a subscript 6 on the right-hand side in a molecular formula, that will tell you how many carbon atoms there are. So in this one, there are 12 hydrogen. There are 6 oxygen. So when you're reading a molecular formula, the subscript number represents how many of that given type of atom are present in that molecule. For example, O2, because that 2 comes after the oxygen, it means there are 2 oxygen in this molecule. H2O, there are 2 hydrogen. Now you'll notice that after it doesn't say O1, you never put 1 as a subscript, so it's O with no subscript represents a single atom. So H2O is 2 hydrogen and 1 oxygen. C6H12O6, which you're going to see a lot in this course, is 6 carbon, 12 hydrogen, 6 oxygen. H2, as you can imagine, means 2 hydrogen, and H2O2 means 2 hydrogen and 2 oxygen. There are 3 ways we're going to talk about bonding atoms in this mini lecture. We're going to talk about ionic bonding, covalent bonding, and hydrogen bonding. We're going to go into each in depth. Ionic bonding is where an atom is going to it will gain or release an electron to its neighbor, and then because they are then charged, they will be attracted to each other. Covalent bonding occurs when an atom shares a pair of electrons, and then hydrogen bonding occurs when usually it's a hydrogen atom in one molecule is attracted to an oxygen atom in another molecule. To understand bonding, we have to understand the octet rule. Atoms want to be stable, and they are most stable when their valence shell is full. For most atoms, that means having 8 atoms in their valence shell. There are 2 exceptions to this rule, and yes, you need to know the 2 exceptions. Hydrogen and helium, they are both in that first row on the periodic table. That means they have 2 electrons fill their valence shell, but all the other ones have 8. This is known as the octet rule. You want 8 electrons in your valence shell to be stable, except hydrogen and helium that only want to a grand total of 2. If you look at this carbon dioxide molecule, the red represents oxygen and the number of electrons. So oxygen has 6 valence electrons, 1, 2, 3, 4, 5, 6, which means it's not stable. If it has 6 valence electrons, it needs 2 more to become stable. So it shares electrons. In this case, it's going to share with carbon. Carbon has 4 electrons in its valence shell. That means it needs 4 more to fill it up. So it shares 2 electrons with oxygen. So now you can see surrounding the oxygen, there are 8 electrons. The other side, that oxygen molecule is sharing with carbon to get a grand total of 8 surrounding it. And because carbon is now sharing 2 pairs of electrons, 1 pair with the oxygen on the left, 1 pair with the oxygen on the right, it also has 8 electrons. Every atom in this molecule is stable. Covalent bonding happens when the atom whose valence shell isn't full shares electrons with the atoms around it to fill their incomplete valence shells. This example shows carbon, which we know needs 8 electrons in its valence shell and has 4 total valence electrons there, sharing electrons with 4 hydrogen. Now, hydrogen is one of our exceptions to the rule, right? It only needs 2 electrons to be stable. So carbon is sharing electrons across the board. So you can see 8 electrons surrounding carbon, and each hydrogen has 2 electrons, making it stable because it's the exception to the octet rule. Now, remember, I just peppered this lecture with periodic tables because I want you to recall that you can count the number of valence electrons by counting the number of columns. So that first column has 1 valence electron, which means it needs 7 more to be stable. That's a lot. The second column has 2 valence electrons, so it needs 6 more to be stable. And then we're going to skip all the way across that gap over to boron, number 5, and that's going to be column 3 that has 3 valence electrons, needs 5 to be stable. Carbon has 4 valence electrons in that next column, so it needs 4 to be stable, and so on. Take note of that final row all the way at the end, column 8. Column 8 has helium, neon, argon, krypton, xenon, and radon. All of these gases on this end already have full valence shells. They already have 8 shells in their 8 electrons in their valence shell. That means that they are all stable. They will not bind with other elements readily because they don't need to share. They're already fine. They are termed the noble gases. Now, we could spend our lives drawing out valence shells over and over and over again. I can tell you, I know this is chlorine just because I know what the picture is. But you can count the number of electrons to figure out the number of protons present in a neutral, electrically neutral atom, and then determine that's the atomic number so you can figure out what it is. But this is chlorine. You'll notice the valence shell has 1, 2, 3, 4, 5, 6, 7 electrons. Because it has 7 electrons, how many more does it need? It needs 1 more. And then off to the left here, you've got a proton and an electron. 1 proton we know is hydrogen, hydrogen being the exception to the octet rule. It needs a grand total of 2 electrons to fill its shell. The easiest thing for these 2 atoms to do to become stable is share their electrons. So here we can see 2 electrons being shared, or a single pair of electrons being shared, between chlorine and hydrogen, forming a covalent bond. They are sharing electrons. To represent that bond, that single pair of electrons, we draw a single line between the H, the hydrogen, and the chlorine. So H line Cl, and that line represents 1 pair of electrons being shared, or 2 electrons total being shared. Single bonds are not the only way we can connect these atoms. You could have double bonds where you're sharing 2 pairs of electrons. Or triple bonds, where you're sharing 3 pairs of electrons, that you can see there with the nitrogen. As far as strength goes, single bonds are pretty strong. Double bonds are stronger. Triple bonds are strongest. Single bonds have a little bit more elasticity. They have a little bit more distance between the two atoms. Double bonds have less distance, and then triple bonds are very, very tightly close to each other. So single bonds have a little bit more movement, but they don't have the strength of double and triple bonds. So if we're looking at structural formulas, these tell us about the bonding relationships. So O2, 2 oxygen, has these 2 lines connecting them. What does that mean? That means they have a double bond, otherwise known as 2 pairs of electrons, or a grand total of 4 electrons. Here, hydrogen and fluorine bond. They have a single bond, so a single pair of electrons, or 2 electrons are being shared. Hydrogen, oxygen, and hydrogen share a single bond between the hydrogen and the oxygen. So a pair of electrons is being shared between that hydrogen and oxygen, and a pair of electrons is being shared between the other hydrogen and oxygen. And then those nitrogens have a triple bond, as we just saw, which means they are sharing 3 pairs of electrons, or a grand total of 6 electrons. Of these, the strongest would be the nitrogen triple bond. The weakest would be the single bonds. So though we write out these these structural formulas on paper, remember, paper's 2-dimensional, but molecules are 3-dimensional. Form determines function. Each bond represents a pivot point. So you can have you're trying to draw what's a 3-dimensional structure on a 2-dimensional page, and it's much harder. It's easier to visualize if you model it, or were to create, like, say, a 3D model in the computer. Like on the left, you can see a 3-dimensional rendition of DNA that forms a twisted ladder. Or on the right, you can see, I think it's hemoglobin, with lots of twists and turns and curls and this big open area in the center. The forms of these molecules ultimately determine what it does. Because DNA has that double helical structure, it's got strong bonds, that it's very stable, and it provides areas where other molecules can bind to it. So its form always determines function. Yeah, I don't know why I put a periodic table here. It's just there. Finally, we have, when we're talking about covalent bonds, I want to talk about a special instance called the polar covalent bond. To understand polar covalent bonds play a major role when we talk about water. It's going to be a huge factor. So to get polar bonds, we have to talk a little about electronegativity. And electronegativity is a concept that comes up again and again and again. Electronegativity is the ability of an atom to attract electrons that are in the bond with another atom. Oxygen is extraordinarily electronegative. In the image on the screen, you see oxygen has an electronegativity of 3.44, hydrogen of 2.2. That means that oxygen is pulling electrons toward itself. It may not steal the electrons, but the electrons are going to hang out more with oxygen than they do with hydrogen. So if you have 2 atoms with differing electronegativities, one of them is pulling the electrons closer to them than the other. This means that if the electrons are hanging out with oxygen more, that side of the molecule where the oxygen is slightly more negative, because you're more likely to find an electron there. The hydrogen have a less propensity to have the electrons around them. So that side's going to be slightly more positive. This leads to what are known as poles. So you have a negative end and a positive end. And as we know, opposites attract. So when you bring polar covalent molecules together, you might form new types of bonds. And that's where we talk about hydrogen bonding. When you have 2 molecules interacting with each other, one way that they do that is hydrogen bonding, where the hydrogen in one molecule, in this case it's water, is a positive charge, a slightly positive charge on that side, and the oxygen on another water molecule has a slightly negative charge. So they hold on to each other tighter than other molecules necessarily would. Opposites attract. You'll notice that hydrogen atoms don't orient themselves so they're attracting other hydrogen atoms because likes repel. This is what ends up giving water a lot of its really cool properties that we talk about in the next mini lecture. And then another class of bonding is ionic bonding. Sometimes, rather than sharing electrons, it's easier for atoms to just sort of let go of or take in an electron. For instance, sodium here. Sodium has a grand old total of 1 electron in its valence shell. That's right, 1 electron. That means it needs to pick up 7 additional electrons. That is extraordinarily difficult to do. It's much easier to just let it go. Let it drop away. If it releases that electron, it becomes a positively charged ion. You've lost a negative, so minus a negative is a positive. Fluorine, on the other hand, fluorine has 7 electrons in its valence shell. It only needs 1. If it happens to be in an area where sodium is letting go of electrons, it can just take that electron in. Well, fluorine then would pick up a negative charge. So plus a negative, and you get a negative ion. Any atom that has a charge is termed an ion. So here we have sodium and chlorine. You may know NaCl, right? Salt. The sodium, to stabilize its valence shell, can lose an electron, and now it has 8 electrons in its valence shell. Chlorine needs to pick up an electron. Well, sodium just dropped it, so chlorine picks up its electron, and now it has 8 in its valence shell. You have a positively charged sodium and a negatively charged chlorine. When those positive and negative charged ions interact with each other, you have ionic bonding. There are certain terms for these bonds, for these ions. It's an anion if it's negatively charged. It's a cation if it's positively charged. You got to just remember it. There's some dumb ways I've come up with over the years, like anion sounds like onion, and onions give you bad breath, and that's negative. It's a way of doing it. Cations, they have the word cat in there, so I guess if you like cats, that's a positive thing, and if I don't know, if you don't like cats, running over cats is a positive thing. However you want to remember it, just remember it. But ionic bonds form when cations interact with anions. Yet again, the periodic table. Ionic bonds are very easily broken down by water. And water, interestingly enough, is the principal environment of the cell, the principal environment in which life occurs. So our next discussion is going to be all about water and how water plays a role in promoting life. So we've got through 3 bonds: covalent bonds where you share electrons, hydrogen bonds where a hydrogen atom in one molecule is attracted to a different electronegative, atom in another molecule that's got a different electronegativity, and ionic bonds where a cation and an anion interact with each other. It's a lot, I know. Last bit, free radicals. You may have heard of free radicals before. Free radicals are unstable ions, and they have extraordinarily high electronegativity. That means that they pull electrons to themselves. They steal electrons from atoms that are already in a molecule. This can happen through exposure to chemicals or to radiation. They can even be created by your body. The thing is, whenever you take an electron away from a molecule, it will then change the shape or the form of that molecule. And if the form of the molecule changes, so does its function. Usually it becomes non-functional. Free radicals can cause an enormous amount of damage to the body, and they're implicated in a lot of different diseases. So your body needs to stop free radical formation, or prevent free radicals from stealing electrons. And the way that happens is through antioxidants. Antioxidants are atoms or molecules that can freely donate electrons. So if they encounter a free radical, they can just be like, here, have an electron, be cool. They're like, I always think of them as the Easter bunny of the cell. They go around just handing out candy. So antioxidants are going to donate electrons to free radicals to prevent them from changing the shape of other molecules by stealing their electrons. They stabilize free radicals. You get these through vitamin C and through vitamin E. Those are very common antioxidants, but there are lots of different ways of doing it. Your cell produces them all the time to protect your body. So there we go. We've got all the different types of bonding. We went thus far from subatomic particles, protons, neutrons, electrons, to atoms, the individual elements, to those atoms and elements coming together to form molecules through hydrogen bonding, covalent bonding, or ionic bonding. Now we're going to, broad picture, we're going to look at chemical reactions. Chemical reactions occur when one or more substances is changed into another. So here we've got carbon dioxide and water are being converted into products of sugar and oxygen. That is the photosynthesis principle right there. I'm not going to go into a lot of depth on chemical reactions at this stage. We're going to talk in depth about some chemical reactions later in the course. And in fact, you're going to see this slide again in a little while. But it's important to note that all chemical reactions require a little bit of energy. And this is one reason you have to constantly take energy, food, into your system. In a living organism, most of these reactions require a catalyst, something to speed up the reaction without itself being altered or consumed. These reactions are going to keep moving. They're going to keep happening until it reaches what's known as chemical equilibrium, where the amount of products being created equals the amount of reactants being created or products being destroyed. And then importantly, harkening back to an earlier slide, most of these reactions in living organisms involve reactants and products that are dissolved in that awesome solution known as water. Water is going to be key to life, the formation of life, because it has such a phenomenal and unique chemical properties. And that is what the entire next lecture is about. So we've got how atoms individually now come together. We've got, in the last lecture, we talked about protons, neutrons, electrons making atoms. Now we talk about how atoms come together to form molecules. So they can be bound using ionic bonds, which is where a cation interacts with an anion, a cation being a positively charged ion, so it has one missing electron or more, and an anion that has one or more extra electrons. They're going to be attracted to each other to form an ionic bond. Covalent bonding, where you're sharing electrons to fill your valence shell, or hydrogen bonding, where an atom in one molecule interacts with an atom in another molecule that has a differing electronegativity. If two atoms are covalently bound, but they have entirely different electronegativities, electronegativity being the propensity of an atom to pull electrons to itself, they will form what's called a polar covalent bond, where in some places the electrons will tend to congregate more. For instance, in water, oxygen's more electronegative, so the electrons hang out by oxygen, and that makes that side of the molecule more negative. The other side, lacking the electrons, that's where they happen not to be, will be slightly more positive. So you've got poles, and those poles lead to some really cool properties that we'll talk about in the next lecture. And then some molecules are called free radicals. They're extraordinarily electronegative. They steal electrons like crazy. And when they steal electrons from molecules that are stable, that molecule begins to lose its form. And if it loses its form, it loses its function. To combat free radicals, we use antioxidants, which donate electrons that stabilize the free radical. For all of these, we have to recognize that atoms are the most stable when they have a full valence shell. So for most atoms, that means 8 electrons in the outer shell. It's called the octet rule. The exception to this rule is hydrogen and helium, which require only 2 electrons. Yes, you have to know that distinction. So most elements require 8 electrons in their outer shell to be stable. except for hydrogen and helium, which require two. And then, of course, at the end, we began talking about chemical reactions in which a reactant or two or more reactants come together to form a product, or a reactant breaks down to form multiple products. Something is happening to the reactant that causes it to become the product. This process will require energy, and it usually needs a catalyst, something to speed up that reaction. They also tend to occur in water, and they will keep going on until that process reaches equilibrium. There we go. Content review questions are here to focus your studies. Next lecture in this series is going to be all about water, so bear with me. I'm going to jump right into it. I guess you could hit pause and stop listening at this stage, but whatever. You might be really into it like I am and just keep going. See you soon.